presented by Caltech.
Good evening. In 1752, Benjamin Franklin wrote to Peter Collinson of the Royal Society and described his famous experiment in letter 11 of observations on electricity. As soon as any of the thunder clouds come over the kite, the pointed wire will draw the electric fire from them, and the kite with all the twine will be electrified, and the loose filaments of the twine will stand out every way and be attracted by an approaching finger. And when the rain has wet the kite and twine so that it can conduct the electric fire freely, you will find it stream out plentifully from the key on the approach of your knuckle. At this key, the file may be charged, and from electric fire thus obtained, spirits may be kindled, and all the other electric experiments may be performed. The sameness of the electric matter with that of lightning, as Franklin would put it, is old hat to us today, as is the familiar image of a key on a kite in a thunderstorm. Yet 260 years ago, it was a beautiful and unexpected demonstration of the link between heavenly phenomena and terrestrial experience, made real through meticulous experimentation and rich and detailed observations. It also came with the satisfying bonus that the trapped fire in the Leyden jar could be used as a source for further electric research. On September 14, 2015, LIGO recorded the whisper of two black holes coalescing far across the universe and back in time, connecting the heavens and the earth for our own day. It was a glorious statement about scientific persistence and discovery, and a wonderful example of how the right mix of people and technology can change the world. The LIGO effort captures the essence of our dreams for Caltech. We want to be the place that takes risks when the scientific and technological payoffs can be large, and have the resolve and ingenuity to succeed. The signature of the gravitational waves picked up by LIGO is an image as redolent for the 21st century as the kite and key flying in a thunderstorm was for the 18th. A good deal of the news coverage focused on LIGO proving Einstein right. There is a pleasing aspect to the confluence of theory and experiment, 1915 and 2015, but this misses the most profound aspect of the discovery. We have opened a new window on the universe, and we are positioned for further surprises emanating from the cosmos. In the aphoristic venue for which Franklin also was famous, he instructed that energy and persistence conquer all things. We celebrate this evening the thousands of researchers who held on to an extraordinary vision over 4 decades until it could be realized. We hear the universe in a different key because of their energy and persistence. It's now my honor to turn the stage over to the experts and invite the panel to come out.
So 12 days ago, Caltech, MIT, and the LIGO scientific collaboration announced the first detection of gravity waves here on Earth. On September 14th of last year, ripples in the fabric of space-time emitted in the final fraction of a second before 2 black holes merged into one rang through the LIGO detectors in Hanford, Washington, and Livingston, Louisiana. This event was the culmination of many decades of work by thousands of scientists and engineers Its detection was the result of one of the most ambitious scientific projects ever undertaken, and it's also the beginning of an exciting and fundamentally new field. Tonight, we've gathered 8 scientists who have worked on LIGO in various capacities. They're going to take you on a journey through the project's history, to the events of September 14 and what the detection means, and finally, looking to the future. So starting out tonight, Kip Thorne and Barry Barish are going to talk about the history of LIGO. Kip's involvement goes back to before LIGO's beginnings, to when the very first ideas for how to detect gravitational waves were being formulated. In the New York Times article about the discovery, Kip is described as, I quote, the evangelist for the field of gravitational waves, which he recently told me may in fact be his greatest contribution to science. Kip, a theorist who prefers to work with just a few students and postdocs, became one of the founders of what is NSF's largest project. So he realized that the quest to detect gravity waves would require entering big science mode. And he told me that he gritted his teeth and moved on. So you have to admit, Kip, it was worth it.
It was worth it.
The 3 scientists who founded LIGO, Kip, Ray Weiss of MIT, and Ron Drever, didn't have any clue how to make a big project happen. This took many people, starting in 1987 with a cosmic ray physicist named Robbie Vogt, who was the PMA division chair and then the provost, and he was just finishing off his term as provost. So he decided he should do something really challenging, which was to become the founding director of LIGO. And Robbie deserves a lot of credit for getting this project established. So LIGO went through many growing pains, and it was decided that someone with big project experience was needed to shepherd LIGO through the construction of the interferometers. So it was on Christmas Day of 1993 when Barry Barish, an eminent particle physicist who had built many large collider experiments, got a call from then PMA division chair Charlie Peck, asking if he could come out to Santa Monica and visit with Barry. Now, Barry said this was very unusual of Charlie and had absolutely no idea what he wanted. He thought maybe he was coming out to console him about the demise of the superconducting super collider, which Barry had been a leader of, and it was just canceled. But Barry did what every good faculty member does when the division chair wants something and said yes. And so Charlie went out and they went on a long walk on the beach and reminisced. And at the end of it, Charlie said, well, President Everhart and I would like you to consider taking on the leadership of LIGO. Barry said it took him about a microsecond to say yes. And he shepherded the project for many years, from 1994 to 2006. So, Kip, why don't you take us back to the beginning?
So, of course, this begins with Albert Einstein 100 years ago when he formulated his general theory of relativity, which says that gravity is due to a warping of space and time. Einstein, 6 months later, made the prediction that, using his general relativity theory, that there should be gravitational waves created by objects in the distant universe that should be bathing the Earth. And now, Einstein, a few days ago, told us what he thinks of LIGO's detection. But Einstein, 100 years ago, didn't think it would be possible, and he said so in his paper. He didn't think that gravitational waves would ever be detected based on what he knew about sources then and technology then. Of course, that was a long time ago. The first person to really attempt I forgot to tell you what gravitational waves are. I got to tell you that first. So a gravitational wave, as it propagates past you, it will stretch space in one direction and squeeze space in the other direction, perpendicular to its propagation direction. And then the stretch and squeeze will oscillate back and forth between one axis and the other. The first person to attempt to detect gravitational waves was Joseph Weber in the 1960s, using a different technology and technique than LIGO uses. Joe in the late 1960s, announced that he was seeing evidence of gravitational waves, but the evidence unfortunately did not hold up. But he, in fact, was the pioneer of this field, and for me personally, he was an inspiration. In the early 1960s, I went for several days hiking in the French Alps with Joe, and we had long discussions of the kinds of science that might ultimately be done with gravitational wave detectors and the technology of gravitational wave detection, and I was hooked. And so when I came to Caltech on the faculty in 1966, yeah, that's me. Very few people have ever seen that chin. So when I came to Caltech in 1966, I started to establish a research group working on the theory of gravitational waves, the theory of black holes, the theory of relativistic stars. In parallel, Ray Weiss, whom I had met at Princeton when I was a graduate student, he was a postdoc. Ray Weiss moved to MIT on the faculty, and Ray began to conceive the basic ideas for the laser interferometer gravitational wave detectors, or interferometers we just call them, or gravity wave interferometers. Although the outline of how such a detector might work was conceived earlier by somebody else. In fact, Ray is the primary inventor of this because Ray, in a real tour de force in 1972, went in and examined, identified all the major noise sources that such an interferometer would have to deal with, and described how they could be dealt with, and did calculations to estimate what sensitivity you could get having dealt with them, concluded that you needed detectors or interferometers that would be kilometers long, and then you would have a real chance of success. That, to me, is perhaps the most important and exciting technical paper that anybody has ever written. Ray Weiss then was followed. He started to build a prototype detector, and that was followed by prototype detectors motivated by him in Scotland and in Germany. And in Scotland, Ronald Drever, and I forgot something else. I need to tell you a little bit about how these detectors work. What you do is you have mirrors that hang from overhead supports along the right-left direction and the in-out direction. When the gravitational wave comes down from overhead, it pushes the mirrors apart on the right-left direction, squeezes them together on the in-out direction. And then at the next half cycle, it stretches in the in-out direction, squeezes in the left-right direction. And that stretch and squeeze is monitored using a technique called laser interferometry that Mike Landry will talk about a little bit later. So shortly after Ray invented this, and as the experimental efforts were getting started in Europe, Ron Drever in Glasgow invented several key ideas for improvements on Ray's design. And we were so impressed here at Caltech and so excited by this field of gravitational wave science that we brought Ron to Caltech in 1979 to start an experimental program to go hand in hand with a theoretical gravity wave program that I was leading. We then also brought to Caltech Stan Whitcomb in 1980 to work with Ron in leading this, and Stan and Ron together built a 40-meter prototype interferometer that is still a major R&D instrument for LIGO. Stan is going to be the last speaker here today. He is currently the chief scientist of the LIGO laboratory. In parallel at MIT, Ray Weiss and his team carried out, with Stan's help, a feasibility study for a large-scale, a multi-kilometer long interferomemeter. The prototype at Caltech was funded by NSF, but only after Caltech had put in about $2 million of its own funds to get the thing started. And you think about how much that has inflated, $2 million from then until now. It is very impressive, the enthusiasm and the backing that we got from Caltech, from the faculty, from the administration, and from the trustees, a backing that has never faltered at all between then and now. At MIT, then the feasibility study was brought to completion, and we went to NSF, Ray, Ron, and I, with results from various prototypes, including the Caltech prototype, and the results of the feasibility study. And in concert with NSF, we created the LIGO project, Ron, Ray, and I, with Caltech, MIT, and the National Science Foundation. And that backing from NSF has also been unwavering since that day. So in 1984, then the LIGO project came into being, and it was led then from 1984 to 1987 by a troika of Weiss, Drever, and Thorne. Troika in that era was a disreputable Russian word that described a dysfunctional leadership, which was a very accurate description of our leadership. If we had continued as the leaders, LIGO would have been a disastrous failure. Fortunately, we were rescued by being fired and Robbie Vogt taking over as director, as Fiona said. Now, before I turn this over to Barry, I want to make a personal statement. Since the announcement of these LIGO's detection of gravitational waves, I've gotten far more credit for this than I deserve. I actually pulled out of day-to-day involvement with LIGO in the early 2000s. The credit for this belongs to the other people who are here on the stage with me, and the hundreds of LIGO scientists and data analysts who have worked together to make this happen. And I also then, in turning this over to you, Barry, I want to thank you for having taken our small-scale project and brought it into a big science mode in a form that has been tremendously successful. In fact, LIGO, the modern LIGO, really is, the structure of it is due far more to you than anybody else. I believe, I've been told by a number of other people, that you have been the most skilled and effective leader of large science projects that the physics community has ever seen, and LIGO has benefited tremendously from that. Barry.
Well, I'm going to, in a few words, try to tell you how we turn this into a project, and then we'll see what kind of project it is and what it's produced and what it can do in the future. And as Fiona said, in the mid or late 1980s, the NSF actually supported the team led by Robbie Vogt to make a proposal to them, and that proposal was finished in 1989. We still look at that proposal as a model of what this would be, with a lot of insight into the ideas that we have now in LIGO. That went to the NSF. In general, the NSF liked it and responded very well to it, and ended up at least taking the first step, which is to decide that it was serious enough that they could look into doing the siting of it. Well, the scientists here at Caltech thought maybe a good site would be, I think, the Edwards Air Force Base. Stan was involved, and the team at MIT would have liked Southern Maine. You can see from the picture that it didn't end up quite there. As the NSF requested, 18 proposals came in, and in some unknown way, the NSF director and the political system decided on these two sites, which you'll hear about today. They're very different from each other. One is high desert in Hanford, Washington, and the other is in the swamps of Louisiana. So technically, they're extremely different, yet we've made them so they're basically identical instruments. Notice that there's two instruments. So the first question, which should be on your lips, is why are there two? And why did we have two from the beginning? The speed of light is such that these two instruments, 3,000 kilometers apart, will take 10 milliseconds to go from one to the other. So anything coming from somewhere in the sky has to hit the two of them within 10 milliseconds, plus or minus 10 milliseconds. And we use that as a constraint that nothing that gives background on the Earth could do. And so this was the first reason, was to make sure that we could have confidence that whatever we saw in a detector was indeed this new thing, gravitational waves. So we decided to make two detectors. The next thing that happened is that, like a lot of big projects, it stumbled around from 1989 till 1994, when, as you heard at the beginning, I was asked to step in. I decided very quickly to join, and then found out soon after that Kip and I had to go testify to the National Science Board and convince them that we knew what we should do and what we could do to build LIGO. Somehow we succeeded, and LIGO was funded in 1994. So it's been 22 years since then, and I want to re-emphasize one thing. It's the biggest project the NSF's ever taken on. It's not maybe the biggest now, but it's close. And we've gone through things like 2008, 22 years is a long time. The NSF budget's gone up and down, and they've never wavered. We've gotten what we were set out to do all the way. And if you ask what they've gotten back until 2 weeks ago, is a few limits that we think are significant, but hardly worth the money that was spent. Training a few graduates, a lot of graduate students maybe, but they stood by us, and the idea that the NSF would take this high-risk endeavor, support it as a line item in Congress for all that time, is truly impressive, I think, for the support of American science. So we started constructing right away. They give us money, we asked for it, we started constructing. This is the beginning of construction in Livingston, Louisiana. There's already a scientific decision we had to make at this point. We had 2 sites, as I said, and the question is, how do you align the arms on one site compared to the arms on the other site? There's really 2 choices. You align them along the same way, ignoring the 16-degree curvature of the Earth, or you make them at an angle, a 45-degree angle with each other. And there are arguments both ways. If you made them at 45 degrees from each other, then you have the ability to determine something about gravitational waves like electromagnetic waves, and that is the polarization. If you line them with each other, we lose that ability, but we have the ability, which you'll see in the next talk, to demand that not only that you got the signal within 10 milliseconds, but that they look essentially identical in the 2 sites. And that was a choice we made, knowing that there would be more sites in the future that could help us do the polarization. So that was what we did next. And then we started building, and I want to try to give a flavor of how we went about this. At this point, we had really no deep idea of how to get to where we are today, and yet we're supported to do that. So we had to take an attitude that's different from the life that I had before. In particle physics, you build a big detector to go on a big machine and leave it there and exploit it, and maybe make some changes in a big shutdown, but not very much. You have to know what you're doing. If you put something in space, that device has to be really made right, put up, and you do what you can do with it. We couldn't do anything like that with LIGO. So the attempt at the beginning and the strategy was always to have much more what happens in a small physics lab. That is, that you develop things as you go along. It's a hard thing to sell. It's a hard thing to do as well. So what we did, starting here, is to create the infrastructure. The main part of the infrastructure for us is a big vacuum system. It's shown in the top slide. It's 1.2 meters in diameter, a total of 16 kilometers of high vacuum. It's the largest high vacuum system in the world, and it's our laboratory. So we made it big. A laser beam doesn't fill that up. So we can run multiple laser beams down and have whatever expansion we need in the future within the same laboratory. So that's in the spirit that I said. The lower right-hand diagram shows this long beam pipe in a minimal enclosure, which is what we built. So things were starting smoothly, but we had our hiccups. This is the lab inside. And again, it shows, I'm going to point out one thing in it. It shows the same thing. There's a person for size. These big tanks that are shown is where the heart of the instrument goes. The mirrors, the lasers go in a separate place. The suspension system, the ability to isolate yourself from the Earth. And you notice both to the left and to the right, there's a vertical piece that closes down. It's called a gate valve. And this was a special gate valve that we had made for these large vacuum pipes so that we could work on the whole instrument, change it, evolve it, with never bringing the whole system up to air, this high vacuum system. Again, that was trying to build in the ability to evolve the system. This is what they look like built. And the same photograph, I don't remember when these were taken, are the same today as they were 10 years ago. So as we've developed the instrument, we haven't had to redo what Advanced LIGO is not a different facility, it's a more sophisticated instrument within the same facility. So this is the laboratory as it looks now. And as we developed this, we found that we had some other needs. Those needs were that even as strong as the team is at Caltech and MIT, and we grew a lot, and we had a lot of money and hired some very good people, we had a lot of deficiencies. We didn't have enough expertise in data analysis, we didn't have enough work in computing, and even in the work we needed to develop the future systems, we didn't have enough. So we created the thing called the LIGO Scientific Collaboration. It's thrived and grown to almost 1,000 scientists around the world. The little flags are where the members are of the scientific collaboration, and it works very democratically. LIGO Lab is what we belong to, which is a subpart of the system and basically has the fiduciary and the responsibility for the equipment itself. Lastly, I just want to dwell on this. This is the sensitivity of the LIGO instrument. The bottom axis is the frequency. The frequency goes from 10 to 10,000. Those are hertz. It's the same as your ear. So on the Earth's surface, the quietest place to do science or to listen is the audio band, and you'll hear some audio simulations. We don't do anything audio, but we have the same problem that at very low frequencies, the Earth shakes too much, and at very high frequencies, we can't sample fast enough, just like your ear, and so that's what cuts us off. The top bar is the evolved best, the sensitivity that we can get is how far down you go toward the bottom of the graph. The top band is the sensitivity that we had after many years with what's called initial LIGO. So what we did is improve it in an evolutionary way, and then we held back on what we needed to make a final big jump. And the big jump was to, for example, use active seismic isolation, not passive, to use a much more high-powered laser and so forth. And you'll hear about some of those. We then started to turn on the advanced LIGO, and it's the middle band. The bottom band is what we're approved and designed to get to. So the message I want to give here is what we've just done is not the end of the story we're already approved for, let alone what we can do in the future that we know about, which Rana will talk about. When you look at this graph, what you should realize is that when we make an improvement of a factor of 2, lowering the line a factor of 2, that actually tells you how far out we can look in the universe, factor of 2 further. But a factor of 2 further is a factor of 8 in volume. So we gained very fast in how much we can see, and therefore in the rate of gravitational waves. So even though we've seen such a fantastic event, which we're going to listen to about now, it's easily going to open up over the next years into a much more robust field where we can do more like astronomy than a basic physics experiment like we've done. So now we can pass it on to Mike.
Yes, thanks, Barry. So the next section of the discussion is going to be about the discovery. And what it means scientifically. So of course, the action started on the ground at the interferometers in Livingston and in Hanford, and Mike Lander here is LIGO's detection lead scientist, and he's joining us from Hanford. Mike started as a Caltech postdoc in 2000, and at that time, he figured that the detection was 10 years away. Turned out to be 16, which is still within typical error bars in astronomy. So Mike is going to tell us what it was like to be on the ground on September 14th. Now, Alan Weinstein here, like Barry, started out life as an experimental particle physicist and was wooed to get into LIGO data analysis by dreams of black holes and neutron stars. Now, LIGO scientists weren't the only ones to be excited on September 14th, because every time LIGO gets a detection, it broadcasts that fact out to many astronomers who've signed up to look at the skies and try to see if there's any associated flash of light in the optical or radio or X-ray or gamma ray. And Mansi Kazawal is leading, our newest astronomy faculty member, is leading Caltech's efforts to try to find the first counterpart of a gravitational wave source. Now we know these were two merging black holes, which shouldn't have an optical or infrared counterpart, but in the future, there will be sources that have counterparts. So Mike, why don't you tell us what happened on September 14th?
Great. Thanks, Fiona. So we're here to celebrate this first direct detection of gravitational waves by LIGO in the laboratory. So let's step back and think about the source first off. 1.3 billion years ago in deep space, two black holes revolving around each other, each black hole about 30 times the mass of our sun, and in the late stages traveling over half the speed of light, merged in a wildly cataclysmic event, yielding the emission of gravitational waves. And these distortions in space-time race throughout the universe at the speed of light, and on September 14th, pass through the Earth, and were detected. And we then denote it GW 150914, the year and the month and the day. I'm going to tell you a little about this detection and the detection process, but I'm just giving you a snapshot. The LIGO scientific collaboration and the Virgo scientific collaboration are over 1,000 people, so they all have their stories. So we begin ours at the two observatory sites. On the left-hand side, you see in the evergreen state of Washington, where I'm located, the Hanford site, the LIGO Hanford Observatory. On the right-hand side, near Baton Rouge, the LIGO Livingston Observatory. And really, LIGO as an observatory functions as two detectors working together in cooperation and in collaboration, and the data are analyzed coherently. So we really need both detectors in this detection process, as Barry mentioned. You also saw in Barry's talk the L of the interferometer, of each interferometer, is defined by this vacuum envelope. You have 1.2 meters in diameter, a tube that runs the 4 kilometers in length. So that punches a massive hole in the atmosphere. It's held at the 10 to the minus 9 torts, an exquisite high vacuum, a real tour de force of engineering. And inside that vacuum envelope go our detector components. We inject laser light into the interferometer, and inside are housed our mirrors. The mirrors are suspended on suspension systems and seismic isolation platforms. There are beam splitters and baffles, and ultimately there are photodetectors which the light from the interferometer lands on and ultimately tells us about the changes of the length in the arm and ultimately gravitational waves if they should pass. The two things we need to do with our detectors, if you want to think of it in real simple terms, are to make the laser light very pure, so pure in amplitude, pure in frequency, and the mirrors very still. If you establish those two things, you have a chance to see the passage of a gravitational wave. We don't actually know when they're going to pass. We go into an observing mode, and you may or may not see them if the signal is loud enough relative to your noise. So how does one detect a gravitational wave with an interferometer then? We'll look at the schematic of a Michelson interferometer, in which we have a laser, and laser light is incident on a beam splitter, which is sent down the arms. And then if the arms change in their length, we read that out at the output port. Kip told us that gravitational waves squeeze along one axis and then the other. Here, laser light, or electromagnetic radiation, marches down to an end mirror, reflects off, and then propagates back to the beam splitter. The beam splitter then sends a sum of the light from one arm and the other arm to the output port. And if those arms change length, then the light from one arm is delayed relative to the other, and that changes the way the light sums at the output port. If it sums constructively, you leak a little light through, that's shown as red here. If it's destructive, it's dark. The astrophysics of the source, the astrophysics of those binary black holes merging, is encoded on the light in the interferometer at the output port. And that's read out by some in-vacuum photodiodes, which convert the light signal to an electrical signal, which ultimately goes to our computers. In September 2014, we were in an observing status at both interferometers. We had emerged from an arduous 4-year process of installing the advanced LIGO detectors and over a year's worth of commissioning, in which commissioning teams are staying late and working into the night to cause the light to resonate and to lower the noise in the interferometer. And in September 2015, we were in this state of observation. And here we have a log from William Parker, who was the LIGO Livingston operator who was on shift that night at 4:05 in the morning, in which he notes the interferometer is in observing mode, the seismicity is quiet, and the weather is clear. All good and necessary requirements for a good detection of gravitational waves. At Hanford, much the same thing was happening. The last scientist on site was Caltech graduate student Evan Hall, who logged about 10 minutes after this his experiments for the night, and then he departed the site. 20 minutes after this, the last scientists at Livingston were Robert Schofield from the University of Oregon and Anna Maria. So maybe Anna Maria, you can tell us how you almost scuttled the first gravitational wave detection in history.
So it's great to be part of that exclusive club. So Robert and I were running some tests that we had been running all week. And so we had a large list, and we had gone through our essential tests. And so at about 2 a.m. or so, we stopped to reconsider and see if we had done everything we wanted to do. And then we had kind of a wish list of maybe interesting tests. In this case, we were debating about at 4 a.m. or so whether to do car injections, which means we take a big truck and we drive it next to the buildings, and we brake at 5-second intervals really sharply, and we time it with a GPS synchronized watch, and then we look for that pattern of 5-second intervals in our data. And that helps us limit traffic around the site. But the watch had desynchronized from GPS, and it was probably not off by more than a second, but it was just the last straw, and it was late, and we were tired, so we just said, let's go home. Thankfully.
That's a great decision, great decision. When Robert and Anna Maria left the site, GW 1509-14 had just passed Mars and was 20 minutes away. At about 4:50 in the morning, it passed through the Livingston detector and modulated the arms by about 1/1000th the size of a proton. And then 6.9 milliseconds later, it passed through Hanford and did the same thing. And my counterpart at Livingston, Brian O'Reilly, never hesitates to tell me that Livingston indeed saw it first. So full marks to them. Within 3 minutes, the signal was found by online codes. And it was entered into a database. The codes were written by Sergei Klimenko in the University of Florida. And postdocs at AEI noticed that there was this event logged in our gravitational wave database. And you see here the kind of thing that's in that database for this event. You see 0.2 seconds worth of data on the right-hand side from the Livingston lab, on the left-hand side from the Hanford lab. On the vertical axis, you see frequency, and that ranges from about, well, the signal is in yellow, and it ranges from about 40 hertz up to 250 hertz or so. And it's increasing in amplitude and frequency, so you'll hear this played by Alan. It makes a whoop sound, so we call it a chirp. So the AEI postdoc saw there's a chirp in the data. It's either a real gravitational wave or it's something we've injected. So we make a test called injections where we know the waveform of gravitational waves from a given source, from general relativity, we know the response to the detector, and we can inject those into both Hanford and Livingston detectors and modulate the arm lengths just so that analysts can tease out this test gravitational wave that we've injected into the machine. And it's an end-to-end test, really useful, detector, calibration, detector characterization, analysis, people, tests everything. We also have a flavor of this test, which is called a blind injection, in which we don't tell the analyst that we've put it on the machine. But we do have to be in a blind injection phase. So when I woke up early on Monday morning, the 14th, I saw that we have a very interesting event email from the analysts at AEI, and I thought, well, that's probably an injection. It looks like an injection. It's too good to be true, right? I raced into the lab, and I cornered our blind injector, Jeff Kissel, and I said, are we in a blind injection phase? I couldn't ask him it was against protocol to ask him if he actually put something in the detector. And to my everlasting amazement, he said no, and we discussed a little more. It was clear there was no injections on the machine. So this took it from the sort of, in my mind, a DEFCON 4 level to sort of a DEFCON 1, and we had to understand what we had. At Livingston, Brian O'Reilly froze any changes on the instrument for about a month. We did the same at Hanford to build some background. And we launched this rapid response protocol, which was brand new. And we combed over the data that day from the instrument, the timing, the calibration, whether people were in a building or not, all of these things. Ultimately, the collaboration worked for months to understand that we had a bona fide gravitational wave in the data and not some spurious coupling or some injection or anything else. This is a remarkable result, extraordinary result. It needs extraordinary proof. And so the entire collaboration worked in order to prove that. So Alan's going to tell us about analysis and the results.
Well, I guess I had a similar experience to Mike's. I woke up on the morning of September 14th and dragged myself out of bed in front of my computer, like I always do. And staring at me was this, and some variation on this. And I just couldn't believe my eyes. The very first thing I thought was blind injection, clearly. Made some phone calls, not a blind injection. I connected up with the control rooms at Hanford and Livingston. Everybody said, not a blind injection. I didn't believe it. It's, I don't know if you know the feeling, you spend 15 years working on some amazing new thing, and then you never really believe it's going to happen, of course. And then there it is staring at you in the face, and the only thing you can think is, I'm not going to get any sleep for the next 3 months. And that's what this little wiggle was sort of telling me. Okay, you can see that the waveform, this is called a waveform, and it's the oscillation is on top of noise, you can sort of see, and it's going from a low frequency to a higher frequency and a higher amplitude, and then it falls. Okay, it goes from the lowest frequencies that the LIGO detectors are sensitive to, which are also the lowest frequency that your ears are sensitive to, about 20 hertz. And then it swoops up to, in just a short time, over the course of 0.2 of a second, to about 250 hertz, which is the frequency of an open B string on a guitar. And we call this frequency rise a chirp, as Mike mentioned. It goes like whoop, like that. Now, gravitational waves are not sound. But since LIGO operates in the audio band, we can take the detector output, put it into a speaker, and listen to it. Now, as you listen, I'll play it. As you listen, keep in mind that the signal is in the detector noise, so there's noise there. It's also only very short, only 1/10 of a second long, and it's damped, kind of, so it sounds pretty much like a faint thud. You might even have a hard time hearing it in the noise. But we can also play the sounds at higher frequencies, that better fit the human hearing range, and then you should be able to hear the chirp. So let's see if we can make this work. So here's that at the end, and let's play the sound. Gee, I don't hear nothing. Hey, you guys back there.
Well, I don't know, Rana told me earlier that he was excellent at making chirps, so.
You think I should do mine first?
Yeah.
Yeah, go ahead.
So I'll do the original one first, and then I'll do one.
Yeah. Clear your throat.
It goes on for a while. And then skip ahead, and then boom.
That's what it sounds.
Okay, you
That's
guys can detect something the fraction of the diameter of a proton, but apparently we can't get the sound to work, so I guess we'll just have to go on.
That was a non-spinning black hole. And
Do it up in frequency.
if you stay later, I do a whole spin. So shift it up in frequency. That's better if you do the higher frequency one. No? And you don't want to do it? Boop.
But
That's as far as I go.
so the little boop part at the end is really important. I'll explain that later.
It's hard.
So Rana did a very good job. I really appreciate that since the sound here isn't working so well. But what we really heard from gravitational waves as transduced by our detector is the sound of the vibrations of space-time itself. And it marks the end of the silent era of astronomy. Now, this event was found by looking at very short signals in the LIGO frequency band, any kind of short signal above the noise. But we can also look specifically for waveforms like this. Let's see if I can, well, okay, I'll go back. Waveforms just like this from binary black hole mergers as predicted by Einstein's general theory of relativity. We can be much more sensitive to very weak signals when we know their form. Of course, we don't know when the signal will come. We don't know what direction the signal will come from or what the black hole masses or other properties are. So we actually have to search over all possibilities all the time, which we do. That's why we have lots of computers to do this. But also, we need predicted waveforms that are as accurate as possible. And that means solving Einstein's equations is field equations in the regime in which they are very hard to solve. Actually, this video here, maybe I can get it to play, looks like a cartoon, but it isn't. It's two black holes orbiting each other, surrounded by, well, in the background there's stars that are being distorted and lensed by the black hole's gravity. And this is actually not a cartoon, it's a supercomputer simulation, and a very non-trivial one. Around black holes, gravity is so strong that it becomes a source of gravity itself. This is what mathematical physicists call nonlinearity, and it's what makes the equations extremely difficult to solve. You need very powerful computers and lots of mathematical ability. Not only is this event the strongest manifestation of gravity ever observed, it's also the most rapidly changing. So we slowed it down for this video here, but the black holes, before they merge together, are moving at half the speed of light, just before they merge into a single black hole in a gigantic roiling storm of strongly curved spacetime. And it's nothing but strongly curved spacetime. There's no matter here, just mass and energy. And in these extreme conditions, they radiate enormous amounts of energy, but only in the form of waves of curved spacetime, gravitational waves. Nothing else comes out. No light, no matter, no light. Black holes are black, even when they smash into each other. This is not an easy thing to even predict with Einstein's equations, but it's been done. Physicists at Caltech and elsewhere have managed to do this immense calculation using supercomputers only in the last decade or so. What we found is that the signal that we observed from this one event matches wonderfully with the prediction from the numerical calculations that are the solutions of Einstein's theory for two black holes orbiting. What this tells us is that the black holes that are predicted by Einstein's theory really do exist. Confirmation of the existence of black holes. And this discovery is not just a triumph for experimental physics and for observational astrophysics. It's also a triumph for the analytical and numerical solutions to general relativity and for Caltech's world-leading group that has been doing this for 20 years, founded by Kip. But we use these waveforms not just to find what we are looking for. Having these theoretical models doesn't just improve our ability to detect the signals, these weak signals. It also means that we can test the predictions of general relativity in the extremely strong field and rapidly changing regime where it's never been tested before, and where it's the most interesting, at least to physicists and astrophysicists. And this event, this one event, passes all those tests beautifully well. It doesn't rule out competing theories of gravity. For now, it's just a test of the consistency between general relativity, the theory, and the observational data. In the future, we'll be able to test against many alternative theories, so stay tuned to that, for that. Also, with this prediction, because now that we have a theory that explains what this waveform looks like, we can extract astrophysical information, the properties of the source. And we can do that pretty well. The masses and the spins of the black holes, their sky location, their distance, et cetera, and so on. So from this, we infer that these two black holes have masses of around 29 times the mass of the sun, 29 solar masses, and 36 solar masses, respectively, while being no bigger than Southern California. So let's see, the total mass is 29 plus 36, that's helped me out here, about 65 solar masses. Can you remember that number? Okay, remember that number, okay. Now these masses, by the way, are significantly higher than most theoretical astrophysicists ever expected to see from black holes. We know of a bunch of black holes, stellar mass black holes, in our galaxy, about 20 or so. They're all about 10 or 20 solar masses. None have ever been seen with such high masses. So it really came as a surprise. Already, with just one event, we are, and in the future we will, learn much more about the origin and evolution of black holes from events like this one. Now, as Mike mentioned, the black hole binary merger that we observed is more than 1 billion light years away. They merged more than 1 billion years ago when multicellular life was just forming on Earth, long time ago. These waves have been traveling since then, at the top speed allowed by spacetime, which is also the speed at which light travels through space. And they only just reached us last September and kept me up since then. So we can also use this to infer the mass of the final merged black hole. Let me see if I can play this video again, and you can see them merging together. And that's about 62 solar masses. So let's see, what was the total mass again? 65, and the final mass was 62. Where'd the other 3 solar masses go? This merger event released 3 solar masses worth of gravitational wave energy by E equals mc squared, about 5% of the total mass energy of the entire system. This is one of the most efficient conversions of mass to energy known. If you're a fan of quantum gravity, for example, it corresponds to the emission of 10 to the 80 gravitons. At peak luminosity, that's energy release over time, well, over the last 1/10 of a second of that merger, this event outshined, in gravitational waves, outshined all the light and other forms of electromagnetic energy from all the stars and in all the galaxies in the entire observable universe, by a factor of about 50. So these kinds of events are the most energetic in the universe that we know of. And we've never noticed them before, until now. Now we're starting to actually hear them. Okay, this is just the beginning. We'll be seeing more events like this as we continuously improve the sensitivity of our detectors, as Rana and Stan will describe. So stay tuned. And having more events doesn't just mean more events to the bank. It really helps us understand black holes and massive stars very well. The reason is, if you're in ordinary stellar astronomy, it really isn't possible to observe a star, for example, throughout its life, birth, evolution, death, and in some explosion. Instead, we observe many stars at many stages of their life, and then we try to piece together the whole story. That's what astrophysics is all about. With events like this, not ordinary stars, but merging black holes, we'll be able to map out the population, the properties, the history, and the evolution of black holes and massive stars throughout the universe. And this will tell us a lot about the astrophysics of massive stars. Now, these are binary black holes. And in addition to binary black holes, in the future, we expect to also be able to detect gravitational waves from the mergers of other compact objects, in particular, the mergers of binary neutron stars. Now, neutron stars are not like black holes. They're a lot more complicated. They're essentially atomic nuclei, but with the mass of the sun and the size of Pasadena. Incredibly dense. And unlike black hole mergers, these kind of binary neutron star mergers make a lot of light. In fact, they're the likely sources of short gamma ray bursts, which we routinely detect with space telescopes from across the universe. They're insanely bright. And they make afterglows that can be observed with optical and radio telescopes on the ground, hours, days, even weeks later. You'll hear about that effort from Mansi shortly. And these events also release huge amounts of material, neutron-rich material, into interstellar space. And this is likely the source of the elements heavier than iron, like my wedding ring. Still shining. Now, my body is made of carbon and oxygen and nitrogen. These are elements that are forged in the core of stars, and they're stardust from a supernova that exploded some 6 billion years ago, leaving behind a dead neutron star and a lot of matter that formed our sun and planets and us. But my ring probably came from 2 such dead stars, merging together in a second death. I'm stardust, but my ring is neutron stardust. So we're not just learning about extreme, exotic phenomena in our universe far removed from typical human experience. With these observations, we'll also be learning about the origins of the stuff that we're made of. Nancy will tell you more. Binary neutron stars merging together and spitting out a lot of material. That's us.
All right, thank you, Alan. So now I'd like to request everybody to please close their eyes for just a few moments.
She really means it.
Okay, thank you. All right, you can open your eyes now. So I have a very simple question for you. Do you know which one of us on stage actually clapped? Okay, our ears heard a sound, but our eyes didn't see it. So we know the sound came from somewhere on stage, because that's where the microphones are, but we don't know exactly where or who it came from. So now let's take this analogy forward. We just heard that advanced LIGO heard the merger of 2 very massive black holes. And this happened somewhere in this big banana on the sky that you see with these colored contours. Now, we don't know where in this banana this happened. Now, as Alan just told you, black holes are very black, not much light associated with them. But very soon, and Rana promises that, we're going to see lots of neutron star mergers with advanced LIGO. And when that happens, when you have an abundant supply of neutrons, if some of them escape and beta decay, or if some of them combine and form these very heavy elements like gold and platinum, and that subsequently decays, all of that can power a flash of light. And if we can catch that flash of light with our eyes, then we can pinpoint exactly where in this banana, which galaxy did that explosion happen in. And as soon as we know which galaxy, we know the precise distance, and we know the environment in which this catastrophic merger happened. And that, in turn, means we can compute the luminosity, the energetics, the calorimetry, really get to the heart of the astrophysics of the event. And wouldn't it be nice if, in addition to finding that flash of light, we find it so fast that we can unravel all the astrochemistry as it happens? So actually get spectra where we can see the lines of gold and platinum with our own eyes. Then this theoretical idea that we have that Alan's wedding ring was made in these binary neutron star mergers, because we don't know where else it could be made. We've never seen it actually in real data. This question can be answered, and Alan would no longer have to scratch his head and puzzle over where that gold came from. We have the opportunity to find it in these cosmic gold mines and cosmic platinum mines. So let me tell you next how we are gearing up to find these cosmic gold mines. And we use eyes way more powerful than the 2 eyes that we have. We are using the eyes of the Caltech optical observatories. So let me take you first to Palomar Observatory, This is a very short 130-mile drive southeast of Pasadena, and I invite all of you to please visit. This beautiful mountaintop is where the action begins. So every single time that LIGO hears a gravitational wave, the telescopes in the Palomar Transient Factory completely robotically, completely autonomously respond to this gravitational wave. So LIGO tells us that it happens somewhere in this big banana on the sky. And this robotic telescope with a very, very wide angle camera, within a few hours will just go and image that entire area. And a few hours is too slow for you, then don't worry, because next year we are building an even bigger camera on the Austrian 48-inch telescope called the Zwicky Transient Facility. Then we can image this whole swath in just a few minutes, so we'd be an order of magnitude more sensitive. But that's just step one, which is going and getting data on that big banana on the sky with a telescope, which is a very, very powerful eye. The next step is applying some real-time software machinery to go through all of that data and find out where are those new flashes of light. Where in this data are flashes of light that have never been seen before, flashes of light that are spatially and temporally coincident with that gravitational wave trigger. And you may be surprised, but the universe is a very dynamic place. It doesn't present us with just one new flash of light. It presents us with thousands of new flashes of light denoted by these yellow dots. So how do we go from that to one? We know that the LIGO flash of light is fading very, very fast, possibly in less than 1 day. So we have less than 1 day to go from thousands of candidates to the one real one. So the way we do this is we make all of our telescopes work in tandem, orchestrate this follow-up campaign to try and identify which one is the real one. So after the Austrian 48-inch telescope, which is our discovery engine, is done, we hand off to the robotic Meyer 60-inch telescope on Palomar Mountain. Then we hand off to the Palomar 200-inch Hale telescope on Palomar Mountain. And this list of thousands comes down to about 10. Then we're in trouble, because a few hours have already elapsed, and the sun is about to rise at Palomar. So how do we beat sunrise? How do we keep this game going and go from 10 candidates to one candidate? So for that, we have to thank the rotation of the Earth. And Caltech is leading the growth relay of networks of telescopes around the world. So what we do is we just go west. So west of California is the Pacific Ocean. Hard to put a telescope in there. But luckily, soon enough, there's the island of Hawaii with the mountaintop of Mauna Kea with the mighty Keck telescopes. These are the biggest eyes on the sky that we have today. So Caltech's Keck telescopes can then get us a very timely optical and infrared spectrum. Remember, the nighttime there is 3 hours longer or later than in California. So we have that much more time to beat sunrise. Now, the spectrum that Keck gets us is actually, spectrum is truth. It is literally the chemical thumbprint of this flash of light. This is our first opportunity to look for lines, bumps and wiggles, that correspond to gold and platinum. Once Keck is done, then we hand off to the rest of the telescopes in our network by going west to Japan, then Taiwan, then India, then Israel, then Sweden. So we can build a full optical and infrared picture. But that's not enough. What we also do is we use a SWIFT satellite to get X-ray and ultraviolet data, and the expanded Very Large Array in Socorro, New Mexico to get radio data. So we really try and get a panchromatic picture of these 10 candidates in hand to figure out exactly which one is truly associated with that gravitational wave. So the game is on. The challenge is very tough. We're trying to find a needle in a haystack, and all we have is 24 hours. The good news is that at least 8 times we've done this successfully with following up fast transients associated with Fermi gamma ray bursts. So Caltech is ready, and the 21st century gold rush has just begun.
Okay, thanks, Mansi. So the final section of tonight's discussion is going to talk about the future of the miraculous machine that is LIGO. LIGO is the most precise instrument on the face of the planet, and there's many more sources that it's going to detect, but it's going to get even better, more sensitive and more capable in the upcoming decades. And to talk about this, we have 3 scientists from the LIGO project. Anna Maria Effler, who was a Caltech undergrad, Caltech class of 2006, is joining us from LIGO Livingston, where she's now a postdoc. So I just learned recently that LIGO scientists at parties like to introduce themselves to each other by saying their LIGO age, which is how long they've worked on the project. So Kip, by definition, is the oldest by LIGO age. But Anna Maria is 9.5, so one of the youngest. And Ron Adhikari, next, did his PhD at MIT, and we recruited him to Caltech, eventually as a faculty member, to work on LIGO's advanced detectors. And Ron is going to tell you how LIGO is going to be made even more sensitive. Finally, Stan Whitcomb is going to talk about the worldwide network of interferometers that will come online in the next decades. Now, Stan retired on September 15th of last year. And as far as I can tell, he's held every position conceivable on LIGO. But Stan denies any conspiracy in the date of his retirement, one day after the detection. However, he had already agreed to chair the detection committee for Observation Run 1. So imagine his surprise when on the day of his retirement, he realized he would be working as hard as he ever had in his life and on his own dime. So, Anna Maria?
Thank you. So before we look towards the future, let's look at what we have right now, because that's also pretty impressive. So I want to tell you first about how sensitive our detector is, and also what are some of the noise sources that affect us, and how we deal with those noise sources. So when I say noise, I mean something like, I'm trying to hear someone scratching their nose in the back of the room while you're all screaming at the top of your lungs, except probably much worse than that. So I'm going to use this video to relate the LIGO sensitivity. How well do we have to measure these arm lengths to the size of a proton? So this is a hydrogen atom, and there's the electron spinning around the blue proton. And we're going to zoom in on that. So the atom's about 10 to the minus 10 meters, and let's assume the proton's about 10 to the minus 15 meters for this argument. So we're zooming in, and now we're sitting on the side of a proton, and that tiny motion, that is the kind of motion that LIGO has to detect. So we can detect distances of about 1,000th size of the diameter of a proton. So, exactly. So sensitive has kind of two meanings, right? It means precise, but it also means easily offended. And our detector is kind of both. So how do we make that happen? What are some of the tricks that we use? So one of the tricks that we use are pendula. And so I'm going to use Rana's shoe over here as a pendulum. Thank you. Just to demonstrate this little concept. So here's how a pendulum works. So if I move very slowly at low frequency, the shoe is moving just as much as my hand. So imagine this is the mirror and this is the suspension point, and I'm trying to isolate the shoe's motion from my hand. Now if I move very quickly, the shoe kind of can't keep up, right? My hand is moving much, much faster than the shoe. And so that's the trick of using pendula. We can isolate at high frequency. And when Barry showed his spectrum and said our detection range is from 20 hertz to a few kilohertz, that's where we're taking advantage of our pendula. And that's why we're limited at low frequency. But from Rana's shoe to real life is kind of a big step. So LIGO uses 4 stages of pendula, and so this isolation effect is multiplied. So that chain in the middle up there, that is our suspension. And it doesn't even look like any form of pendula, and there's all this hardware around it. And all I'm trying to show here is that LIGO is also basically an engineering work of art. And another piece related to that are our optics. So our mirrors are about 40 kilograms, they're about this big, of fused silica, which is a type of glass, and they are hung from also fused silica fibers, so also glass, laser welded onto the optic. Now, that mirror in the picture doesn't look like much of a mirror, right? We can see through it. And that is because we use infrared lasers, and to our infrared laser, that is almost a perfect mirror. Its reflection is 99.9999995%. Your usual bathroom mirror is about 90% reflective. So our mirrors are so much better than any mirror that you normally see that only one company agreed to even try to make our mirrors to our specifications. Moving on. All right, so what are some of the noise sources that affect us? All our hardware is in vacuum, right? So you say, okay, you're fine. In vacuum, no one can hear you scream. But that's not quite true. So if you have your mirror in vacuum, or whatever, some object, and it's being held there by some elaborate setup that's eventually connected to the outside, then any noise from the outside can then follow that chain back in and shake your mirror. Or if you're bouncing lasers around inside the vacuum, a little bit of stray light can leave, hit the walls or something else, come back and pollute that pure light that we're trying to use to detect gravitational waves, right? So what are some examples of these noise sources? I usually like to think of them in terms of two rough groups. One is sources of noise that don't even let us run at all, the detector, and one is a category of noises that pollute our sensitivity. So some examples are earthquakes. Earthquakes almost anywhere in the world, if they're large enough, can stop us from running because they vibrate the ground at very low frequency, like a 100-second kind of period, but they move it a lot. Ocean waves, you didn't expect that probably. Ocean waves move the ocean floor, so they just knock on it, at about a 5-second period. And if there's storms, that motion is amplified and propagates everywhere over the Earth. And we see it in our detectors, and sometimes those motions are simply too much, and our interferometer cannot run at all. There's other noises. A plane can come by and rumble and send an acoustic wave. Or lightning storms can happen and send off little magnetic booms when lightning goes off. Or even inside our lab, we have to worry about things like our air conditioning is vibrating the walls of the building, and so on. So how do we protect ourselves against all these things that may appear louder than a gravitational wave? So first of all, we pepper the place with sensors. So all those little symbols in this diagram are different sensors for different ambient sources of noise. Okay, so we check what's happening, but how do we know how our instrument is actually affected by these sources? So then we make our own noise. For example, for checking acoustic coupling to our detector, we take a giant speaker and we make a lot of noise. And then we look at what we see in the microphone, what's the noise we actually produced, and the gravitational wave signal. And then we compare the two, and we say, okay, we can set a threshold here and say, if the noise in these microphones is lower than blah, then there should be no acoustic effect in our gravitational wave signal. And we do that over and over with many locations and different sources of environmental noise. And so we have, I don't know, something over 100,000 auxiliary signals, not including just ambient noise signals, but other signals related to the detector itself, that are checked when a gravitational wave signal or possible signal is detected. And the signal on September 14 passed absolutely all these tests. So now I will let Rana tell you more about the future.
When the signal came in on September 14th, I was not very excited because a lot of people were excited, people younger than me in LIGO years. And I said, relax, I've been there before. This is probably fake. It was easily a month before I became convinced it was real. And when you're as old, I'm not as old as everyone here, but when you're as old as I am in LIGO years, you live in a world of, there's just no signals, and that's how the world is. And when, it's always been like that. And when, it took a while to convert into this world where now there's something instead of nothing. And immediately I thought, well, if we have one, why can't we have more? Why should it just be one? We should get one per hour, one per day, something. That's how greedy we are. And Anna Maria just showed you all of these real practical limits that we have. But we've started really now to explore how good can we do on the Earth? What's the ultimate that we can one day get? And the reason we want to get to this point is, of course, we don't just want one signal, we want many, many signals. And we want to get signals not just from the nearby universe, but we'd like to get them from the early universe. We'd like to get them from all over the universe to map out what's really going on. And finally, we'd like to measure them so well that we can really test the Einstein theory of gravity. So I'm just going to tell you about a few of the limits, and these are things which we believed were real limits that we would never get past on the Earth, but as you'll see, not so. So one of the issues, as you saw in the previous diagram, is there's all sorts of objects that, through their gravitational influence, limit how well we can do. And Anna Maria listed cows and deer. But before we get to that level, one of the important sources is the fact that the ground is vibrating, and whenever a piece of the ground comes up, just like the moon attracts tides to it and the moon gravitationally pulls on the Earth, the fluctuating ground near our mirrors pulls on the mirrors like so. And so the vibration of the ground, even though we've isolated from it as well as we can, we have no way to isolate the gravitational influence. And so this ground is pulling on the mirror and moving it around. And we think probably, just like in this analogy of the noisy room, the noise which comes from the ground moving is going to be a real limit. But, it's just Newtonian gravity, and we now know that we can calculate even the complications of Einsteinian gravity. So if we knew what every atom in the universe was doing, of course, we could figure out the gravitational force from it and subtract that out of our data. Well, that's tough. But we can do the next best thing. We can take a seismometer, a seismic sensor which measures the ground motion, and stick it in the Earth. That works well. We can measure the ground very well. But we'd like to measure more of the ground. So if one is good, let's use more. So we populate the Earth underneath our building with 100 of these in this kind of a pattern, which we've calculated using sophisticated algorithms. Now, how do we convert the ground motion sensors from so many sensors into an estimate of how much the gravitational force is tugging on the test mass? Well, that kind of calculation, in principle, you could do if you had a army of physicists with a lot of notepads. You could get to this eventually. Or you could be modern about it and use modern deep learning techniques, where we just take all of these data streams, feed it into one big computer, and give it the objective of subtracting the noise out. And after a while, as we've found doing real experiments in the laboratory, this type of technique works just fine. The computer develops its own subtraction algorithm after about 20 to 30 minutes. You can test it out, and you can test it out after it's found its algorithm. Even a month later, it works just fine. So using this technique, really what we're doing by subtracting this gravitational noise out of the data is we're making the environment on the Earth similar to the environment in space, where there's no gravitational perturbations. We're sort of bringing the feel of doing space experiments to the Earth, and which is started off as a project for an undergraduate student 10 years ago, is now a practical, to me, astonishing thing that we can actually accomplish. However, that's not the only limit. One of the limits has to do with the fact that we're using these beautiful mirrors. To me, I never get tired of it. This is, when I was a student, Stan allowed me to be his assistant one day, and I was just in awe at how beautiful the system looked inside. There's all this shiny metal and glass that you can just see through. This piece of glass in particular is so pure that almost no one in the world even knows how to measure how pure it is. It's just beyond the limits of our measurement. And we use it in the LIGO interferometers. And it's been wonderful for us. We have this detection. But like I said, I want more. And what should we do? Well, these numbers, when we talk about these, how to measure a gravitational wave, these numbers are sort of, they seem absurd. We're talking about 1/100000th the size of a hydrogen atom. What does that even mean? How can you measure the motion of something so large to a distance which is so much smaller than an atom? Well, our trick is basically that we average over the motions of all the molecules on the surface. We're measuring so many of them that the individual motions kind of average out. But even still, when they somewhat average out, they don't completely go to zero. And the fact that we're operating here at room temperature means the molecules are moving around with some sort of thermal energy. So what we'd like to do is focus all of this energy into frequencies we don't care about, and then also to use the tools of low temperature physics to cool down the mirror to the point where the individual molecular motions just don't matter at all. And in that way, we'd be able to get beyond the usual experimental limits of room temperature physics. As it turns out, glass is wonderful. People have been studying glass for years and years. But the study of ultra pure single crystal silicon has surpassed that of few silica, of glass, just in the last 20, 30 years or so. So the single crystal silicon made by the semiconductor industry, which we are now riding on the coattails of, basically by using all of their R&D, they can produce mirrors which are so smooth, they look wonderful, they're polished, and they're so large that they're able to work in gravitational wave interferometers. And these things can be cooled down and their properties just get better and better at low temperature. So now we have a technique to surpass the gravitational noise on the Earth, and we have the possibility of using low temperature single crystal silicon mirrors and bypassing the thermodynamic limits on the Earth. But then we get to what felt like a really hard problem, I think, which was, can we get beyond the limits that quantum physics sets for us? And I mean, the immediate answer is no. But you say no, but, and then there's a caveat which I'm about to tell you about. So we know about the Heisenberg uncertainty principle. When we like to measure something really well, the better we try to measure its position, the more poorly we're able to measure its momentum. And that's because the stronger we probe something, it sort of buffets it around and moves its position around. Similarly, if we try to measure the amplitude and the phase of the laser light, the laser field which is coming out of the interferometer, there's a similar uncertainty principle. And so there's some complementary relationship between the amplitude of the electromagnetic field and then the phase of the electromagnetic field. And if you recall the animation you saw earlier, we rely on measurements of the phase of the electromagnetic field to reveal to us the gravitational wave signal, which comes from the interferometer. Now, when you look at the electromagnetic field and it's the way it shows up in our detector, we see it as this pitter-patter, sort of like raindrops on your roof when you actually listen to the data stream which comes out. The discrete nature of light makes this sort of hiss. And so it's sort of like if you wanted to listen to some quiet music in your home when it's raining really hard, it's tough. You have this, raindrops are not quantum, but the analogy only goes so far. But the discrete nature of the light sort of limits the resolution by which you can measure the motion of the mirrors. There's a complementary effect, which is the discrete nature of the light not only limits how well you can measure the motion of the mirror, but when you send that laser light into the system, the fact that it's not a continuous and smooth field actually buffets the mirror around. And in this image, I've used this bouncing ball getting hit by photons, and those photons which are now bouncing off of this shaking mirror are now getting into your detector, and the little thought bubble for the detector is showing what it estimates the motion of the mirror to be, and it's seeing this shaking thing. So not only it's a limit to how well you can measure position, but the light itself buffets the system, and the more light you use, the more the system is shaken. However, we have a trick up our sleeve, which is we only really care about the phase of the laser field as it comes out of the system. And so what we could do, what the Heisenberg uncertainty principle tells us, is we can either measure the amplitude or the phase arbitrarily well, at the expense of the other. So the better we measure the phase, the worse we measure the amplitude. Well, lucky for us, we don't need to measure the amplitude. It just doesn't matter to us. None of that has any information about the gravitational wave signal. So if somehow we could adjust this picture and take all of the noise and squeeze it into the areas where the green bunches of noise are, that would change our estimate of the amplitude of the signal. But if there was no noise in the red or pink areas, then it wouldn't at all influence our counting of the zero crossings of the signal or our estimates of the phase. So that's a wish we have. If we could do that, we'd be in business. So we started looking into this, and I say we, I was in the 6th grade, so it wasn't me. But when I say we, I mean people in Kip's group in the late 70s and early 80s started looking into what's this all about, and how can do we really have to live with this picture of discrete photons bouncing off our system? Is there something more fundamental, and how do we get around this? They looked into this, and people at the time were realizing that empty space is not really empty. You look at it, and it's roiling and bubbling with fluctuations of the electromagnetic field. And this phrase sort of sounds ridiculous. It sounded ridiculous to me when I first heard it, but I will say it to you anyway. This noise, which is there in empty space, the noise of emptiness is getting into our system. And that noise of emptiness, this random fluctuations of the electromagnetic field, interfere with our ultra-pure laser. And that's what produces the fluctuation in the photon number, which are buffeting our mirror, and that's what produces the random pitter-patter of photons on our detector. And so what the challenge is to us is, can we modify the fluctuations of empty space? This also sounds sort of absurd when I say it out loud, but that's really the challenge. Can we modify the fluctuations of empty space in a way that we can remove this noise and get to this picture with all of the noise squeezed into the green parts of the cycle? That's the challenge to us. Well, Carlton Caves, who was a grad student of Kip's in the late 70s, started looking into this, and he decided, yeah, it's true, in fact. There was a group thinking about quantum mechanics at the time, led by Kip and Vladimir Brzezinski, and discussions in that group led to the concept of squeezing. I've been using that word over and over. That's a real technical term. It sounds not, but it is. There's a technique called squeezing where you can change the actual statistics of the quantum vacuum. And we now have practical ways to implement it, and Kip's student from much later in 2003, Yanbei Chen, who's now on the faculty here, has really thought of practical ways for us to implement this in the detectors. And this was a sort of a dream in the laboratory, I would say, in the 80s. Jeff Kimball here showed, working in quantum optics, showed how this could be done on the tabletop in the late 80s and early 90s. And this is a diagram of how it would work. On the top, you see our signal with usual quantum vacuum fluctuations. And on the bottom, you see what happens with the injection of squeezed light. Instead of the noise being uniformly distributed all over, the noise is now bunched up into the areas where the amplitude, where it only influences the amplitude of the signal. And in the places where we would measure the phase of the signal, there is no noise. And this is not, this is just a diagram, but this is not just a diagram. I mean, it's a real thing. We have implemented a real squeezed light system into gravitational wave interferometers and seen real reductions of the quantum noise. So it sounds very fantastical, but it works in real life. So now we've got all of the ingredients. We can remove gravitational noise using sophisticated algorithms, using modern material science and understanding of the physics of crystals. We can remove the thermal vibrations, and by engineering the quantum statistics of empty space, we're able to make better systems with better and better interferometric resolution. Putting all of that together, it puts the picture of the future of this field into a whole new light. That's not supposed to be a pun. Into a whole new light, and which is the reach of these systems now goes far beyond. If we implement all of these technologies, it goes far beyond what we had envisioned for the Earth-based detectors. And as Barry mentioned earlier, the investment in the LIGO infrastructure was pretty grand in the beginning, and that is going to really turn out to pay off. The investment in the mid-90s is going to mean that the future of these detector systems extends at least for another 10 or 20 years. And we can now, I say now, but living in the future, I'm saying now. So we, now meaning soon, we'll be able to implement these technologies and detect black holes out to the edge of the universe. Imagine we have ground-based systems which can detect every single binary black hole system in the universe. And when you go from one to all of them by implementing these technologies. And all of a sudden, you can do more than what you had imagined before by several signals. You have these explosions going off all over the universe, and all of a sudden it's like having a sonar system which you can probe the universe. You find out exactly what's going on in the early universe and the late universe. You can probe the history of cosmic expansion. You can find out about the fundamental nature of space-time, and you can test gravity with such a high fidelity that we will be the ones using these devices to find the next extension to the Einstein theory of gravity. And this is what we will do to improve our interferometers, but what Stan will tell you about is what we can do by adding a few more around the world.
So thank you. What I'd like to do now is turn us not from these individual detectors, but to talk about the global future for gravitational wave detection. Turning back to Monsi's demonstration about how your ear is not a very good sensor of where things are. I don't know if you noticed, but I was the one who clapped and helped her. How many of you got that right? Okay, a few. A gravitational wave detector really is very much like an ear. It's a great detector. It looks in all directions for gravitational waves and sees them from almost all directions, but it doesn't have, an individual detector has very poor ability to say where the waves are coming from. We get our information about where the waves are coming from by having multiple detectors, our two detectors. Radha, could you give me a detector? So our two detectors here are sitting on the Earth, and the wave comes in, it hits first one detector and then the next one. And by looking at the time difference, we can tell what angle those waves are coming in at. What we can't tell is whether they're coming in this way or this way up through the Earth, because they transmit directly through the Earth, or this way at the same angle. So that's what gives that huge banana pattern on the sky that Monsi had to survey. How do we do better? Well, we add another detector. If we add a third detector, we can now look at the time of arrival of the waves at all three of the places, and that will give us not this huge banana on the sky, but a small localized patch. Fortunately, we have some friends, the Virgo project in Europe. It's a project that's about a year behind us. We're hoping that the next time we run this year, or perhaps next year, they will be in a position to run with us. And when we have them operating with our two LIGO detectors, we've got those three detectors, we'll be able to triangulate on the sources. This is a map of the sky. Each of those ellipses shows if you had a wave coming from that part of the sky, how large a region would we be able, how small a region would we be able to identify it coming from? So the places where those circles are small, or ellipses are small, we can localize the source position rather well. So up in the upper left-hand corner, lower right-hand corner, we've got two pretty good regions of the sky where we can identify where the sources are coming, but there's that great swath through the middle where we don't localize the sources very well. Those are, that triangular pattern of 3 detectors does very well at identifying the positions of sources when those sources are coming from near, perpendicular to the plane of the triangle. It does very poorly when it's looking at sources that are coming in the plane of the triangle. And so that line of bad places there, thank you, Rana, but I don't need one yet. So those line of bad ellipses, that denotes the plane of the triangle formed by the 2 LIGO detectors and Virgo. So, of course, it's obvious. What do we do if we want to do better than this? We add more detectors. We have some additional friends. There's a Japanese project called Kagra. It's currently under construction. They're building a detector in a mountain underground. It's got some cryogenic features. It's a slightly more, in some ways, technologically advanced detector, but it's behind us by some 3 to 5 years probably, but it's going to come online. And just last week, we got word that the Indian government had approved a collaborative project between India and the LIGO laboratory to put a LIGO detector in India. India will provide the site, the infrastructure, we will provide the detector components and some of the expertise to help train them. Together, we will operate that site. It's called LIGO India. Because Kagra and LIGO India are out of the plane of that triangle, now no matter where the gravitational waves are coming from, there's no plane of a triangle to give us poor localization. And as a result, we get this kind of a map. So this is that same sky map showing the ability to localize the positions of sources. If this one consists of the 2 LIGO sites here in the US, Virgo in Europe, and LIGO India. And you see that we can find the positions of these sources rather well over the entire sky. Remember how bad it was before? And this is how good it gets when we add LIGO India. So we're very excited about this new development. We see just a tremendously bright future for gravitational waves with this global network. I shouldn't say bright future, a very loud future. We're continuing with that ear analogy. But there's more. Gravitational waves, just like electromagnetic radiation, have different periods, different frequencies. For the electromagnetic radiation, we've got light, infrared radiation, ultraviolet, radio waves, X-rays, gamma rays, all of those things. For gravitational waves, we also have a range of periods ranging from milliseconds. So the gravitational waves that LIGO sees have periods of milliseconds up to maybe 1/10 of a second. And those are coming from sources that have the mass of about 1 to maybe 10 or 30 solar masses. Not very large, but stellar mass kind of objects. If you go a little bit longer in period, to hours and minutes, there's a whole set of gravitational wave sources that come from more massive objects. Black holes that have masses more like 1,000,000 solar masses. In order to see gravitational waves in the minutes to hours kind of periods, you have to go into space. You can't do that from here on Earth. And there's a project called LISA, or currently called ELISA, that proposes to launch a set of detectors into orbit around the sun to detect gravitational waves with these longer periods. JPL has had a long history in this and has made major contributions. We hope that NASA will get involved in this. We'll actually provide some of the funding, and we'll be able to get the JPL scientists involved in that project, and perhaps somewhat triggered by this discovery by LIGO. In addition, you can go even to longer periods, years or decades, and here the technique that's most promising for detecting those is to observe radio pulsars. A pulsar is a neutron star that emits a regular train of radio pulses, maybe 30 a second, maybe 10 a second, and those pulses travel through space to the Earth. If we have radio telescopes here on Earth that measure the timing of those pulses, a gravitational wave striking the Earth will disturb the space around the Earth and cause those radio pulses to be disturbed. They won't come in quite as regularly as they would without that gravitational wave. And we can get the signature of the gravitational wave by looking at the timing of these radio pulsars. Again, Caltech and JPL are involved in pulsar timing measurements. And finally, you can go to even longer periods, up from, say, 100 million years up to billions of years for the period. These are gravitational waves that since the Big Bang may have only oscillated 100 times. But in that oscillation, they left a pattern in the cosmic microwave background, the 3-degree black body radiation that we see. That's a particular pattern that's encoded in the polarization along with the temperature pattern of the cosmic microwave background. Very difficult to detect, but there's a team of people here at Caltech and elsewhere that are working. The team of Caltech here has a telescope and detectors at the South Pole, BICEP 2, and again, we hope that they will be seeing gravitational waves that are coming from the early universe. They would be, in some sense, the signature from the very earliest stages of the universe that we currently have, even earlier than the cosmic microwave background. The gravitational waves were formed there. They left their imprint in the cosmic microwave background, but they came directly from the Big Bang. So we think that the future of gravitational waves is bright. No, not bright, loud. We've got it started. It's going to be really, really big. Caltech and JPL are playing a major role across the entire spectrum. Finally, I'd like to come back and bookmark something that Kip said. This is not an endeavor that 8 people did. This is an endeavor that literally thousands of people have participated in. Certainly much more than 1,000 people have participated in LIGO. I can't mention everybody. We put together a list of some of the key contributors, people who've made major contributions through the history of this, and I just want to point out, I'm sorry if there's anybody's name that we left off. It's difficult to credit everyone, but these are some of the people who've made major contributions in different areas through the history of LIGO. And now I'll turn it over to Fiona for our question and answer.
Okay, well, let's thank all of our panelists. We're going to take questions from the audience. There should be microphones that you can queue up on either side. And while you're queuing up, I'll ask the panelists one question, which is, most of us didn't think binary black holes were going to be the first things detected. And so what are other sources that LIGO might detect, and what would surprise and excite you the most?
Signals from the early universe.
Kip.
Something that we didn't expect, a huge surprise.
Okay, anyone else? Okay, why don't we start on this side?
Just want to say in my 35 plus years at Caltech, this is absolutely the best presentation I've ever seen. I don't know who's responsible for it, but kudos to everybody involved.
Okay, on this side?
Well, congratulations to all of you. I was wondering, at what point do you think LIGO will be listening for primordial gravitational waves? You mentioned after you get done mapping all the black holes.
Primordial gravitational waves are very difficult to detect in the LIGO band, depending upon where they come from. If you just have the standard prediction from what's called the standard inflation model, the gravitational waves from the standard inflation would probably not be detectable by advanced LIGO, maybe one of these fancy detectors that Ron is talking about, but even then I think it's a bit iffy. Our better chance of seeing the cosmic microwave the background, the stochastic background from gravitational waves would come from the pulsar timing or perhaps from a space-based detector. Maybe not LISA, but there's another one that's been proposed that's a different variant that might be having that. But those are still, I think, several years away.
Thank you.
Okay, on this side.
Hi, yeah, so congratulations again. Great series of talks, and it's an exciting result. So my question might be primarily for Mansi. So as Rana loquaciously demonstrated, the chirp less than a second. And if I remember right in your talk about growth, you were saying that there's a time scale of about a day that you might be looking in more optically driven bands. And I was wondering if that's true, and then what the astrophysical drivers that are setting that time scale is.
That's a great question, thank you. Right now what we think would power the electromagnetic emission is, there are a few possibilities. So first, we have a lot of neutrons in this problem, right? We have a neutron star merging with another neutron star or a black hole. Say 2% of these free neutrons escape at relativistic speeds, and they move out fast enough, and then they beta decay. So a neutron splits into a proton, electron, and energy. That happens with a half-life of 10 minutes. So given the numbers of neutrons that we expect, the combination gives you a flash of light that will be fade away on our time scales. So we'll see it with our big telescopes for about a day or a few days. On the other hand, if we have these neutrons clubbed together and make bigger and bigger and heavier elements, then these very heavy elements have a more luxurious half-life of radioactive decay. So that could give us a little bit more than a day, maybe a few days or a week to chase the signal. Trouble is that that's probably a very red signal, which is hard to see because of the intrinsic transparency to these elements.
Okay, it's getting late, so why don't we take one more question?
I noticed on one of the slides that Fritz Zwicky's name was associated with the Palomar Transient Facility. I'm wondering what the connection with him was, whether he had work that was related to gravitational waves. My second question is the MIT Caltech collaboration. Do you see that continuing? Do you see a collaborative ventures or going separate ways?
Okay, Mansi, you're in a good position to talk about the...
So I can answer the first question.
I'll answer the second one.
And so Professor Fritz Zwicky is founding grandfather of time domain astronomy, surveys in general, the very concept of taking a wide-angle camera and imaging huge swaths of sky. So in dedication for this new project that we are developing here, we are just dedicating it in his memory, in his honor, for his invaluable contributions to time domain astronomy as we understand it today.
Very appropriate.
He also envisioned the concept of neutron stars, which was a radical idea at the time.
Discovered
Still a radical
supernovae.
idea.
I mean, so many things, it's hard to list.
Yeah.
So.
About Caltech MIT, this collaboration's worked fantastically well. So there's no reason we wouldn't continue it. It's built in.
Great, thank you.
Oh, okay, so we have one more person. This will be the last
This will be a
question.
2-second answer.
Okay.
Thank you all, congratulations. I think somebody had to ask this question. I understand if you can't answer it, but maybe you can smile. Have you seen any more?
Deadpan.
We frown. He's frowning.
He's smiling and not looking at me. Thank you guys very much. Thank you.
Okay.